Let's calculate a plus b squared. We start by writing it as a plus b times a plus b. We multiply by distributing a times a times b times a, and b times b. When we multiply a times a, we get a squared plus a times b plus b times a plus b times b, which is b squared. Now ab and ba are like terms, they're both ab, so we can combine them. There's two of them, so a squared plus 2ab plus b squared. What about a plus b to the third? Well, we can split it up as a plus b times a plus b squared, and then we recall that a plus b squared is a squared plus 2ab plus b squared. Then we distribute, so we get to distribute a times a squared, a times 2ab, a times b squared, and then b times a squared, b times 2ab, and b times b squared. What results from that? Carefully work this out. A times a squared gives you a to the third. A times 2ab gives you 2a squared b because of the a times a, plus a times b squared, and then you go ahead with the b, plus b a squared plus b a squared plus 2ab squared plus b times b squared, which is b to the third. Now observe that we do have a like terms. 2a squared b plus ba squared is 3a squared b. In this column we also have like terms. You have one of those and two of those is three of those. A b squared plus, then you have your b cubed and you have your a cubed. That took quite a bit of time, but we got it. We could also approach the problem of raising a plus b to the fourth power in a similar fashion. We can split it up, a plus b to the fourth as a plus b times a plus b cubed, and then you recall that a plus b cubed is a to the third plus 3a squared b plus 3ab squared plus b cubed, and then you proceed to distribute. So you do a times a cubed, a times 3a squared b, and so on. After spending a bit of time, quite a bit of time, you end up with your result, a to the fourth plus 4a to the third b plus 6a squared b squared plus 4ab cubed plus b to the fourth. What about if you want to calculate something like a plus b to the 10th, for example? Say a plus b to the 10th. Now if we use the same technique illustrated, we would like to split it up as a plus b times a plus b to the 9th, but then you have to know a plus b to the 9th, which itself will require a lot of effort to complete. So what we propose here is that if we want to expand a binomial to a power, do it with a formula. Is there such a formula? The answer is yes. We know it as the binomial theorem. So here's how the binomial theorem goes. Let n be a positive integer, then a plus b to the power n equals the sum from j equals 0 to n of n choose j times a to the jth power times b to the n minus j power. You can develop this, you can split this up as when j is 0, n choose 0 times a to the 0, b to the n, plus when j is 1, n choose 1, a to the first, b to the n minus 1, plus when j is 2, n choose 2, a squared, b to the n minus 2, plus all the way down up until j equals n, that is plus n choose n, a to the n, b to the 0. Now let's try some examples applying the binomial theorem, the formula that we have here. Our first example will be to expand x plus 2 to the 7th. Now let's observe how we are going to apply the binomial theorem in this case. In this case, the power is 7, so we will have the form of our example would be a plus b to the 7th power. If we apply our binomial formula, it will look something like this. A plus b to the 7th, that's the form of our example, would be the sum from j equals 0 to 7, 7 choose j, times a to the j times b to the 7 minus j. If you break that up explicitly, you end up writing the following terms: 7 choose 0, a to the 0, b to the 7, plus 7 choose 1, a to the first, b to the 6, plus 7 choose 2, a squared, b to the 5th, plus 7 choose 3, a to the 3rd, b to the 4th, plus 7 choose 4, a to the 4th, b to the 3rd, plus 7 choose 5, a 5th, b squared, plus 7 choose 6, a to the 6th, b to the 1st, plus 7 choose 7, a to the 7, b to the 0. That's a total of 8 terms. Now, once you understand that the terms split this way, then you begin your calculations. Now in our case, we want 7 choose 0, 7 choose 1, all the way to 7 choose 7. We can get that using a calculator. We want our a to the 0. Well, in this case, what is a to the 0? It will have to be x to the 0. A to the 1 will have to be x to the first, and so on. And what about the b's? B to the 7 will actually be 2 to the 7th. B to the 6 will be 2 to the 6th, and so on. So let's do a little bit of that. Let's do a little bit of that work. So we are expanding x plus 2 to the 7th, which we know to be 7 choose 0, x to the 0. Here the role of a is assumed by x, and the role of b is assumed by 2, so that will be 2 to the 7th, plus then 7 choose 1, x to the 1, 2 to the 6, plus 7 choose 2, x to the 2, 2 to the 5, plus, once you write enough terms, you notice that the pattern is easy to carry out. In this example, there are quite a few terms, but the pattern isn't a problem. You can sit down and carefully write all your terms as I am illustrating here. I'm intending to write all the terms in this illustration Almost done. So 7 choose 6, x to the 6, 2 to the 1, and the last one is 7 choose 7, x to the 7, 2 to the 0th power. And then what is 7 choose 0? 7 choose 0 turns out to be 1, times x to the 0 turns out to be 1, times 2 to the 7. If you calculate 2 to the 7th, you end up getting 128 plus, let's do one more, let's do a couple more here. 7 choose 1 will turn out to be 7, times x to the first will be x, and then 2 to the 6 will be 64 plus 7 choose 2. 7 choose 2, you can do your little, you can use a calculator, or you can do your little formula. 7 choose 2 is 7 factorial over 2 factorial times 5 factorial. The 7 factorial and the 5 factorial do cancel out. You're left with 6 times 7. 2 factorial is 2, so you can cancel out the 2 with the 6, and then 3 times 7 is 21, so you write a 21 for 7 choose 2, and then you have x squared, and then 2 to the 5th, which is 32, plus, and so on down to the very last term. The very last term is 7 choose 7, which is 1 times x to the 7th, and then 2 to the 0, which also will also be 1. Now once you finish developing each of the terms and perform your calculations, you arrive at your answer, which in this case I have prepared. At the end you end up getting that x plus 2 to the 7 is 128 plus 448x plus 672x squared, and so on, as written in this answer. Alrighty, let's try another example, a very similar example with a small twist to it. In this case, we want to expand the expression 3x minus 2y all raised to the 5th. And this time around we're having a difference, and each of the terms of the binomial do happen to have coefficients. We begin by noticing the form of our binomial to the power 5th is of this manner, a minus b to the 5th. If you want to apply the formula that we have for the binomial theorem, if we want to apply this formula right here, the way we wrote it has plus in between a and b. So when we are repairing that in this problem is rewrite a minus b as a plus negative b, and then directly apply the formula. So you have the sum from j equals 0 to 5, 5 choose j, a to the j. Now this part is what you're going to raise to the 5 minus j, so it's a negative b to the 5 minus j. And if you were to write it explicitly, you get 5 choose 0, a to the 0, negative b to the 5 minus 0, which is negative b to the 5, plus then 5 choose 1, a to the 1, negative b to the 4th, plus 5 choose 2, a squared, negative b to the 3rd, and so on up until the last term, which will be 5 choose 5, a to the 5th, negative b to the 0. Now you can process this a little bit. For instance, here I get negative b to the 5th. The negative raised to the 5th actually makes that a negative in front of the whole term. Is 5 choose 0, a to the 0, b to the 5th. Here negative b to the 4th, the negative when raised to the 4th becomes a positive, so you still have a plus, and then 5 choose 1, a to the 1st, b to the 4th. Negative b to the 3rd, when you raise the negative to the 3rd power, gives you a negative, so that's minus 5 choose 2, a squared, b cubed, and so on as written here. So let's proceed. We get to pretty much use this expanded expression. We're going to apply 3x in place of a. We're going to apply 2y in place of b. So let's see what that results in. I'll do a little bit of this work to see the result of that. So we're expanding 3x minus 2y to the fifth. So let's begin with the minus. If 5, choose 0. The a part is the 3x raised to the 0. The b part is the 2y. The b part is the 2y, and that's being raised to the fifth power. And then plus 5, choose 1, 3x to the first, 2y to the fourth, plus 3, choose 2, 3x squared, 2y cubed, plus 3, excuse me, that was 5, that is a mistake, sorry. So 5, choose 3, 3x to the third, 2y squared, plus 5, choose 4, 3x to the fourth, 2y to the first. Our last term is 5, choose 5, 3x to the fifth power, 2y to 0. I'm being careless here. There are some alternations of signs, so let me correct that. This minus plus, this is supposed to be a minus here, and then plus, and that's a minus. So please do note the correction. I was trying to write this too quickly. And now we're going to do exactly the same thing we did with our previous example. We're going to go ahead and process all this each of these terms by performing calculations. Here we will have to do 5, choose 0, 3x to the 0 would become 1, and then 2y to the fifth becomes 2 to the fifth y to the fifth, and 2 to the fifth is 32. So then you write that down as your the first term of your next step, and then you write 5, choose 1, which happens to be 5, and then 3x times 16y to the fourth. At the end of that process, you will get an answer. I'll leave the details to the audience, the details of carefully computing out each of those terms. At the end, you should check that the result of the expansion of 3x minus 2y to the fifth results in negative 32y to the fifth plus 240xy to the fourth minus 720x squared y cubed plus 1080x cubed y squared minus 810x fourth y plus 243x fifth. We maybe could inspect this one very quickly here. 5, choose 1 is 1. 3 to the fifth is 243, and then you have x to the fifth, and then 2y to the 0 is just 1. So at the end, this term is just 243 x to the fifth, as our answer shows. Alright, one more example. Find the coefficient of x 10th y third in the expansion of x squared plus 5y raised to the 8th power. Now we're going to propose a rather direct way of getting that coefficient. one way of doing the problem, though, would be to go back here to our binomial theorem and write in the expansion. In that case, would be n would be 8, the a part would be x squared, and the b part would be 5y. So you could go ahead and write out the binomial formula, the binomial expansion that you get from the binomial theorem. In the case n equals 8, ab x squared, and b 5y. You could do that, and then at the end, after you spend a little bit of time, you can go and find out which of those terms in that expansion has an x to the 10 y to the third, and then you look at its coefficient. Problem solved. But as I said, in this we're going to devise a rather direct way, which doesn't involve performing the full expansion. What we want to do is this: make use of the fact that each term in the expansion of a plus b to the power n has the form n choose j times a to the j times b to the n minus j. Just looking at the binomial theorem reveals that each of the terms in this sum have that form: n choose j, a to the j, b to the n minus j. So in our case, then each of the terms of x squared plus 5y to the 8th power would have to be of the form 8 choose j. We're now replacing the corresponding quantities of our problem. It will be for n we'll have 8 choose j. For a would have to use x squared, so that will be x squared to the j, and for b we would have to use 5y, so 5y raised to the 8 minus j. So I have written that. So consequently, each term in the expansion of x squared plus 5y raised to the 8th power has the form 8 choose j, x squared to the j, 5y all of it raised to the 8 minus j. Now let's do a little bit of clearing up here, and that will be the same as 8 choose j then if you multiply this out, if you split this up, you get 5 to the 8 minus j. I'm putting it in the front. And if you process x squared to the j, that just gives you x to the 2j by multiplying the two exponents, 2 in j, and then y to the 8 minus j. Now, if we want the coefficient of x to the 10th y cubed, if we want the coefficient of x to the 10th y cubed, then we're going to have to look for the term that has x to the 10 y to the third. That can only happen when j is 5 in this expression, because 2j you want it to be 10. So that means that j would have to be 5 necessarily. So if j is 5, then what? This expression becomes 5 to the third, because j being 5 gives you 8 minus 5, which is 3 as the exponent of 5. And then you have 8 choose 5, and then you have x to the 10 y to the third. Now this problem is clearly rigged. By just plugging j equals 5, we get the term x10 y third. In creating this problem, we needed to specifically not just say x10 and y to an arbitrary power. We do need to say y third, because that's what the expansion produces. Now, to finish it up, you have to sort of pinpoint that that's the coefficient that you're looking for, that 5 to the third a choose 5. That will be the coefficient that you're looking for. And you finish the problem by actually doing the calculation. I am here displaying the results. So in conclusion, the coefficient of x to the 10 y to the third in the expansion of x squared plus 5y all raised to the 8th is 125 a choose 5. Where does the 125 come from? Well, just computing 5 to the third. And then if you compute a choose 5, maybe with a calculator or maybe using the formula for n choose k, you end up finding that a choose 5 is 56, and you finish up by multiplying 125 times 56, which turns out to be 7,000. We're pretty much done with this lesson. That's all.